Okay, welcome to week two of Fundamentals of Nano and Quantum Photonics course, which is offered by Professor Naresh K. Imani from IIT Hyderabad on NPTEL portal. And I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay and also at Institute for Solid State Physics at TU Berlin. So today we're going to cover some aspects of the light matter interaction, which is basically how the light interacts with the matter. It will be a classical oscillator model, which we will try to understand certain equations, how we can arrive at the equation for permittivity, refractive index, polarization, and then we will jump into the light matter interaction in case of metals, where you have the free electrons, something called as Drude-Lorentz model or Drude models. Herein we are going to see the interband and intraband transitions. Okay, for now, what we are going to do is that this is the outline, the course outline, which we are roughly going to follow. And we will be dealing with this week two, which is the light matter interaction, dielectric functions, Krammer-Kronig relations, and other things. So this is what we will be trying to cover in today's section. Okay, these are the references books and the references which, if you are interested, you can follow. Maybe the quantum optics one is a very good book by Mark Fox. And you can all definitely check other books as well. There is one more book called as uh, I guess its name is B.S. Saleh. I guess its name is Photonics or something like Introduction to Photonics, and it covers a lot of aspects about the photonics. So if you are interested, you can definitely go and have a look of this book. So now what we are going to cover today. Definitely, we're not going to cover all of the things which Professor has discussed. He has discussed a lot of things, but we are going to cover at least some of the basics, whatever is given in the assignment section, and whatever is important in all of the I should say the things which have been covered in the week. Okay, so first of all, we have some of the things we're going to cover is, let's say, for example, optical response. The brief outline, which will be something like this, we will be trying to cover the optical response of the materials. Herein, we will discuss about, let's say, the reflection. We will discuss about transmission. We will discuss about absorption, a little bit about scattering, and a little bit about luminescence. This is what basically Professor has started with. And then we will go into discussing, let's say, permittivity. Permittivity. We'll talk about the Lorentz model, which is just like a spring mass system. Same governing equations, and it's the same system wherein you can understand basically the fundamental role of, let's say, for example, the resonance frequency. We can understand the plasma frequency. You can understand plasma frequency. You can understand the damping of electromagnetic waves. You can understand the absorption. Okay, that is basically the damping of electromagnetic waves. And herein you will be understanding basically the oscillators. Let's say, for example, the you might be having the electronic oscillators. The electronic oscillators. You can have vibrational oscillators. You can have rotational oscillators. These are just different degrees of freedom which an atom can have inside a solid. So either it can have, let's say, for example, a vibrations like this, wherein this is the nucleus of an atom, this is the electron. Then, for example, if the electric field, incoming electric field is in this direction, you know that the nucleus will move in the direction of the electric field because it's positive charge, and the electron will move in the opposite direction. So it will be a motion like this. So suppose this is a positive charge, and this is a hypothetical, let's say a spring connected to it, and this is an electron. So this will try to extend, and this will try to compress. It will be compression and I should say rarefaction of this particular system. Obviously, there is no spring. It's just a hypothetical thing we are trying to show you because of the what will happen to the system in presence of the electric field. Because the force due to electric field will be minus E times the electric field. Okay, so this is the system we will be talking about, and then we will be moving into Lorentz model. We will talk briefly about, let's say, polarization, which is basically roughly defined as dipole moment per unit volume. We will see how to arrive at certain relations of the polarization, what it is, what the causality is. Let's say we will talk about causality here, causality, and we will try to think about, let's say, for example, multiple Lorentz oscillators, and then we will talk about Drude model. Again, I'll be briefly discussing all of these. Drude-Lorentz model, not going into the depth because Professor has already talked about it. We will be mostly discussing in the questions. And then we will talk about, let's say, Krammer-Kronig relations. All of these things have been covered by the professor in this week. And we can have finally some optically engineered engineered materials, how we can engineer the epsilon, the mu, the refractive index, and how we can play with them. So that is the brief outline. So now what we are going to do is that, let's say, for example, uh, we are going to start with the optical response of the materials. The optical response of the materials is, let's say, for example, if we talk about, let's say, for example, you have a material and if you have an incoming electromagnetic wave, which is a plane wave solution of the Maxwell's equation, it can be denoted something like, for example, E naught e to the power minus I kx minus omega t, and you can definitely write this k as n omega by c, but and you know this n basically belongs to complex. That means it's some n1 plus I times n2. That means you can write, for example, this n as n plus I times k. So basically this relation can be written as E naught e to the power minus I n omega over c x minus omega t, and you can write it as this will be e to the power minus k omega by c into x. So it will be uh, e to the power, let's say, for example, if you want to compute the intensity, then intensity, you know, is proportional to the amplitude, electric field amplitude square. Then you square this term and you get e to the power minus 2 k omega over c into x, which is e to the power minus, which can be basically written as this particular thing. So this is that this what this is showing is that the intensity of the electric field, the intensity of the electromagnetic wave basically drops with x. For example, this is x, and this is, let's say, for example, the intensity of the electromagnetic wave, which is directly proportional to the electric field amplitude. Then it says that it drops as it goes into the medium. Obviously, now it depends upon what are the values of the k, what are the values of the what are the different absorption coefficients inside the medium. So whenever an electromagnetic wave, let's say this is a medium of, let's say, for example, length L, so this dimension is x. So whenever the electromagnetic wave hits it, it's going to either decay, and some part, let's say, for example, after it decays, it's going to transmit. Okay, here what happens here is that some part can get reflected. Here also some part can get absorbed. That is what basically the decaying part shows. That is, some part is getting absorbed and there is energy conversion. Energy conversion. Because whatever the electromagnetic energy is getting absorbed, it has to get converted into some other form of energy. Okay, because the energy conservation has to be there. So it is not just like electromagnetic waves getting absorbed and nothing is happening. Sometimes, let's say, for example, if the electromagnetic energy gets absorbed in a medium, that gets converted into, let's say, change in temperature. So the temperature starts to increase. Okay, that means the medium starts to heat up. That means the electromagnetic energy has been converted into thermal energy. So there has to be those some form of energy exchange. So this is, let's say, for example, the incoming wave. This is the reflected wave. This is the transmitted wave. So this is the absorbed part. So overall, if we say that reflection plus transmission plus absorption is equivalent to one, because those are the scenarios which are going to happen whenever an electromagnetic wave hits the medium. So for example, there might be reflection, there might be transmission, and all of these scenarios, reflection, transmission, and absorption, they simultaneously occur in all of the mediums. Okay, the values might be low, the values might be less, but they all happen simultaneously. Let's say, for example, you have a metal, and metal, for example, has a property that it is mostly reflective at certain frequencies. So if you have a metal, a shiny metal, let's say for example sodium, or maybe let's say silver, and if you hit it with the electromagnetic wave, you see that most of the electromagnetic wave gets reflected. Obviously, there is some penetration depth of the electromagnetic wave, which is denoted by this. Let's say for example, it penetrates up to certain depth. Let's denote it as alpha, which is 1 over mu. So mu is absorption coefficient. Absorption coefficient. And typically for metals, this absorption coefficient of electromagnetic wave is around 10 to 12 nanometers. So it's very small. So just like you might have talked about something like skin depth. That is basically the skin depth of the electromagnetic wave. But now what you will see here is that you can make these metals, you can change the behavior of these metals altogether. So you can tune the behavior of the metal. Okay. So this will get reflected, but definitely there is some absorption here at this point. And if you, let's say, for example, make this metallic layer as thin as, for example, 10 nanometer, if you make this as 10 nanometer thin, then definitely what is going to happen is the incoming wave is going to get reflected as well as absorbed, and it's all going to get transmitted. And you can measure it. That is the beauty of this. You can do it experimentally. So you can change the thickness of it. You can change the thickness of the metallic layer deposited over certain material, and you can play with these. So what I'm saying is that these all phenomena, reflection, transmission, and absorption, are always present in all of the mediums. You can tune it. You can make one of the quantities higher and others lower, but they are always present, and they sum up to one. Obviously, there has to be, if this is 100%, let's say for example the reflection is 80%, the absorbed part is 10%, the transmitted part is 10%. So they sum up to 100. Okay, so that is the basic notion of it. Now, now what is basically going to happen is that, for example, based on this, you have certain types of materials. You have semiconductors, you have insulators, you have metals, and how do you differentiate them? If for example the incoming photon, there is first of all, in case of semiconductors, there is a band gap. You know about all of these concepts where there is a clear unacceptable value of energy between the minimum of the conduction band and the maximum of the valence band. Okay, so if you draw the EK over this plot, that might look something like this. So this is the bottom of the EK. So this is E versus K. So basically the bottom of this is shown as a band diagram. So you can draw E versus K. This is E versus K. So this is the bottom of this valence band. So basically, if you have E versus K, let me draw it like this. So this is E versus K. So this point is basically shown here, and similarly for the valence band, this point is shown here. So what is going to happen is that there can be electronic transitions. Electron can go higher, and electron can then come back to the original state. And if, for example, the incoming electromagnetic waves energy, if there is some photon coming with energy h nu, if it's less than the energy gap, the photon is basically transmitted. Okay, so photon gets transmitted directly. It does not interact with the medium. Let's say up to a first order approximation, it does not interact. But if, for example, the incoming photon is greater than the band gap, then this photon is basically absorbed. Okay, now what happens during that absorption is a different story. For example, if you have a band gap of, let's say, 1.2 eV, and if the incoming photon has an energy 1.2 eV, it can create the electron hole pairs, and the electron will go at exactly uh, the bottom of this conduction band edge. Okay, and it does not have any excess kinetic energy, or it does not have any excess energy. But on the other hand, if you have, for example, the incoming photon in the same scenario, for example, if I show the incoming photon of 2 electron volts, now what's going to happen is that the electron will go higher, and it will come up to this energy state, and this will be the excess kinetic energy. This is basically the excess kinetic energy. Again, you know all of these things. So the excess kinetic energy will be 0.8 eV. Now, this excess kinetic energy has to be transmitted, or it has to be given to the system, so that electron can come back to this particular lowest energy state, which is the conduction band. And finally, from conduction to the valence band, there will be recombinations. And this particular process, which is basically shown here, this happens in steps. It can either happen, for example, if you have multiple energy levels, electron can go here, then it can come down, and finally it can basically radiatively or non-radiatively recombine, depending upon what type of a semiconductor it is. So it has to give up the extra kinetic energy. And when it gives off the extra kinetic energy, usually, because these are happening in the same energy structure, or I should say, it gives off this extra kinetic energy to lattice in the form of something called as phonons. So whenever the electron comes down, it gives off H omega cube. This is basically the energy of a phonon. Energy of phonon. So whenever it gives energy to the phonons, so the lattice starts to vibrate now. Okay, because of which the lattice starts to heat up. And when the lattice starts to heat up, so you have a temperature increase. Okay, so that is the basic notion of how the electronic transition takes place. Now, what basically happens if you have, let's say, for example, transmission curves. If you have transmission represented as Tx versus, let's say, for example, the wavelength in, let's say, for example, the microns. And for some material, let's say, for example, you have a transmission curve like this. Obviously, it has to be up to 1, and it can start from, let's say, 0. So if you have a transmission curve like this, that means these wavelength values are completely transmitted. This particular wavelength value, there's a dip in transmission. That means there is increased absorption. Okay, there's increased absorption. Okay, so what does it now mean? For example, you can have at this particular wavelength there can be certain other processes happening, because of which there is extra absorption of the incoming beams. For example, this is mostly in, let's say, IR region. Let's say this is visible region, and this is UV region. Okay, so that is the basic fundamental notion of how to read a transmission. This can be even a reflection curve. That will be opposite of it. For example, if the red one is the transmission curve, you can have the reflection curve something like this, not exactly like this. It's like this. Why am I drawing it like this? Like this. There will be, oh yes. So this will be the opposite. This will be the reflection coefficient. The red one is the transmission coefficient. Okay. Similarly, you can play with it. And you need to understand how these absorptions are basically taking place. Now, for example, you talk about the refractive index. Basically, this absorption is determined by the refractive index. And what part of refractive index? Basically, the imaginary part of the refractive index. Imaginary part of the refractive index. So you know that refractive index is basically n plus I k. Let's say I call it kappa. And you can write basically the absorption, which is, let's say, mu, to be equivalent to 4 pi kappa over lambda. So this is the relation between the absorption coefficient, and this is attenuation coefficient. This is attenuation coefficient. This is absorption coefficient. and it has a units of 1 over length. So if you inverse the 1 over mu, you get delta, which is basically the penetration depth of an electromagnetic wave, which is basically lambda over 4 pi kappa. So this is called the penetration depth of the electromagnetic wave. So it's basically the value at which the amplitude falls to 1 by E. Let's say, for example, this is the medium. For example, this is the medium, and it has a length of L, and this is the x direction. If the electromagnetic wave comes, it decays and it decays. For example, this is the maximum value of electric field here. Let's say, for example, E, and the absorption or the penetration depth is the value. Let's say, for example, this value at which the amplitude falls to 1 over E times the amplitude at the initial point. Okay, so this will be the delta, the penetration depth. So the penetration depth will be this much. Okay, so this will be the value of the penetration depth. Otherwise, basically, it's exponentially decaying. So if you consider it mathematically, then exponential decaying curve, it touches the x-axis at infinity. Okay, it just goes on. But you have to consider some definite value. So you consider it as to be 1 by E value, 1 by E of the initial amplitude. So that is basically defined as the penetration depth, and it comes simply from the relation, or what I showed earlier. It comes even from the Beer-Lambert law. You have intensity to be directly proportional to e to the power minus 2 kx, and you can just show from here that it is basically the penetration depth is the depth at which the amplitude falls to 1 by e. Just simple mathematics. So now what happens? There are basically, for example, this absorption. That means if there is imaginary part of the refractive index, it gives rise to the absorption in the medium. Now it turns out that there is a in case of semiconductors, there are two types of semiconductors which also you might have talked about. You have direct bandgap semiconductor, you have indirect bandgap semiconductors. Direct bandgap semiconductors have both the, let's say this is E versus K. They have the conduction band minima and the valence band maxima at the same K. Okay, but in case of an indirect band gap semiconductors, these values, both of these conduction band minima and the valence band maxima are at different K values. So this is, let's say, K1, so this will be K2. Now, how does the transition take place? It does not go like this because the photon does not have the enough momentum to change the K. If in case, for example, the photon is coming, let me not show the photon like this. If the photon is coming with energy h nu, it can basically cause the transition of the electron like this. Okay, not like this. Okay, why doesn't it cause the transition of electron like this? Because the photon doesn't have enough momentum. It has very low momentum. Low momentum. Okay, so it cannot change the momentum of the electron, at least up to the first order, whatever you are going to be taught in this course. Maybe in upcoming courses, you might see certain scenarios where you can do certain things which can change the momentum. But right now, it cannot change. That's why it goes in the pink direction rather than the red direction. So the red direction, it does not go directly to this. The electron goes in the pink direction, reaches here, to an intermediate state, and then another something comes up here, another, let's say, a quasi particle or intermediate particle. Let's say a phonon comes in with energy h omega q. Basically, q is the phonon wave vector. And when the phonon comes in, it interacts with the electron. It causes this electron to go here, and the electron reaches here. That is basically, this is mediated by the phonon mediated process in case of an indirect bandgap semiconductors. But for a direct bandgap semiconductor, the advantage is that the electrons can directly go up, and it can directly come down and emit a photon which is equivalent to the bandgap. So that's why these are good for, let's say, light applications, light emitting applications. For example, gallium arsenide based semiconductors, or other semiconductors which are direct bandgap semiconductors, or gallium phosphide or other semiconductors. So this is, let's say, for example, the case of silicon. That is why for the silicon, even there is a limit in the efficiency of the solar cell you can make, or you cannot make good LEDs out of silicon. The reason is because of there is these phonon mediated processes are involved. So for example, you have then the electron going like this, then you have the phonon coming in this direction, making the electron go in this direction, and finally the electron has to, obviously electron has to then come back to its original state, so the overall electron has to come back here in order to radiate something. So that's why indirect bandgap semiconductors are very bad, because they give off so much heat also. So there is a thermal issue as well because of the involvement of the phonons. So a lot of engineering is happening basically in this field. Okay, so what happens now basically if you have, let's say for example, now talk about metals. Metals are quite unique in the perspective that they have a lot of free electrons. When I say free electrons, they are just like nearly free electrons, and they are obviously bound to a certain system, but they are free in the sense that they are delocalized over the entire surface of the metal, and they act like a free electron, but they are not exactly free, just like an electron in a vacuum or something. Okay, so what happens is basically if you see the reflectivity versus the frequency versus the, let's say the wavelength curve, you see that at particular wavelength or at particular frequency dips, and this particular region is basically the visible region. This is the visible region. This particular region is the UV region, and this is the IR region. Okay, so for example, what happens at this particular at this particular point? This is basically, you can convert it basically into frequency. So if the wavelength is increasing in this direction, so frequency is increasing in this direction. So at this particular point, there is some frequency which is called as plasma frequency. And metals below plasma frequency behaves completely reflective, but the above plasma frequency it starts to absorb. At even the plasma frequency, it starts to absorb. So it's just like it starts to resonate with the electrons oscillations. Okay, so that's what we are going to see in the oscillator model of the Lorentz oscillator model. So you can see that below this it is completely reflective, and above this it is basically it's not reflecting, and at this particular frequency it is basically absorbing at the plasma frequency. So now what is the scenario? The scenario is if you have, let's say for example, let's talk about the Lorentz model. How do we understand how the let's say an atoms in a, for example, a metal. If you have a metal or a semiconductor, you have atoms, and you have with along with atoms you have electrons which are in their orbits or in their particular electronic states. How do you model this particular phenomena, and whenever the incoming electromagnetic wave is coming in? So for example, if you take one of this chain of atoms, you take one of the atoms and you consider an electron here, and let's say for example the applied electric field is in this direction, then you see that the system is going to behave like this. It's going to stretch and it's going to compress. So this will be stretching, this will be compression, because the positive will feel the force in the direction of electric field, the electron will feel the force in the opposite direction. So there'll be compression and rarefaction, and you know that this is just like a simple harmonic motion. You have been teased about a pendulum, mass pendulum system with certain spring constant K, but this is a massless spring, remember that. And you have basically mass, and you know that how you can represent its natural frequency, where this resonant frequency that will be under root of K over M. Okay, and this is the same scenario. It's going to have a solution, let's say a displacement x of t to be equivalent to x naught sine of omega t type of solution, which is the solution of the differential equation of the simple harmonic motion. Now, for example, what is basically driving here? The driving field is electric field. And what is this electric field? This is basically from the electromagnetic wave. Remember that. So remember that electromagnetic wave has the electric field, it has the magnetic field. So this is, let's say, the electric field part. This is the electric field part. Pardon me, I'm not drawing it to the scale. And if it's a transverse electromagnetic wave, then E is perpendicular to B field, it's perpendicular to Z, which is basically the propagation direction. Now here, right now, we are considering only the electric field. Now someone might ask, why aren't we considering the magnetic field? That is also going to have an impact on this atomic system. We will consider it later on. For example, let's first consider only the electric field here for simplifying it. And it turns out that if you have, for example, the driving field as electric field, which is the driving force as electric field, which is basically gives the force to be equivalent to minus E times the electric field, then you can have three scenarios. The first scenario is that if the driving field has a frequency, it has some frequency, obviously, because it's an electromagnetic wave. A plane wave has certain frequency e to the power I kx minus omega t, which is this is the frequency of the electromagnetic wave. So if this frequency is equivalent to the resonant frequency of this system, of this atomic system, the positive charge and the negative charge, this particular frequency. Now, how does K and M, is the mass of this system. Even rather, the better thing would be to represent this M as mu, which will be the effective mass, the mass of the nucleus plus mass of the electrons. That will be the better thing to discuss here. So mu omega naught will be under root of K over mu. Mu is the reduced mass. Okay. So if the incoming frequency is equivalent to the, I should say the natural resonant frequency of the system. So you will see a strong absorption, strongly absorbed EM wave. Okay, this is the resonance occurring, resonance of the incoming electromagnetic wave with that of the natural frequency of the resonance frequency of the system. Okay, so there is a strong absorption of the incoming wave. What is the second scenario? Either the incoming frequency will be much greater than the resonant frequency, or the incoming frequency will be much greater than the much less than the resonant frequency. In both of these scenarios, there is not strong interaction of the electromagnetic wave, not strong interaction of electromagnetic wave. Now, what happens is that because of this, there is some phase lag. Phi I represent as phase. There is some phase lag because of mass. You see that you have an incoming electromagnetic wave, but because there is certain mass associated with the nucleus, there is certain mass associated with the electron. So they are not going to respond immediately. Will be certain phase lag associated with it. Once, let's say, for example, this will tend to stretch it because you see that if you consider only one cycle of this is, for example, electromagnetic wave. So this is the positive cycle of electric field of the electromagnetic wave. This is electric field, and this is the negative cycle of electromagnetic wave because it's a sinusoid. So during the positive cycle, let's say, for example, the electron, you will see there will be a stretching, for example, of the electron, this particular thing. During the negative cycle, these will come closer. These will come closer. So this is going to happen on and on. This is going to happen again and again. This is going to happen again and again. Okay, depending upon how this is going to change. But it's not going to be immediate, because there is certain mass associated with it, mass of electron and mass of nucleus. So there will be certain lag associated with the response of it. So that lag basically is associated with the phase lag of the electromagnetic wave. They associated with the phase lag. Okay. And that phase lag basically gets accumulated over some distance, accumulated over let's say some distance. When you consider many atoms, that phase lag gets accumulated because there is not only one atom, there are multiple atoms. As a result, that phase lag gets accumulated, and this is basically the reason that why light slows down. Okay, so that's why you have the light inside the medium is speed of light divided by refractive index. The light slows down by the amount of refractive index because this can be represented as the speed of light divided by n plus ik. So light slows down because of this particular phenomena. So it gets absorbed, and there is some phase lag associated with because of these oscillators' masses involved. Light itself is a massless thing. It's a photon, but there are masses associated with the atoms as well as the electrons. So it's just like, for example, you have certain positive charges, and the electrons. And if you consider now the multiple oscillators, let's say, for example, multiple oscillators, so you will have incoming electromagnetic wave. So there will be phase lag associated with it, and now that is basically the result. There is a bending of this wave because that phase lag accumulates, and as a result, it gives result in a wave in this particular direction where all of the, let's say, all waves add up in phase, and in all other directions, let's say for example this direction or this direction, they almost cancel out each other. So that's why you will see upon refraction there is a bending in the wave. That is basically happening because of these oscillators are tending to have a phase lag associated with them. Okay, so maybe you can have think about this, what basically I talked about. You can even think about this in terms of mathematics. So now this is basically the electronic oscillator. The electrons are oscillating back and forth. And particularly here, if I talk about nucleus is much heavier than that of the electron. So you can consider the m of E to be much, much less than m of N. So this is almost like a stationary thing, stationary nucleus. Okay, so this is a very common approximation which we use, which we take. So we are considering the relative motion of the electron around the nucleus. So if this is the nucleus, so this is the electron. So electron is basically moving back and forth, back and forth, back and forth. So that is basically the same scenario. Okay, now you can have a vibrational oscillator. You can have a vibrational oscillator. Oscillator. In terms of vibrational oscillator, what do you have? You can have, let's say, for example, if you talk about silicon is having four other silicon atoms to which it is bonded. So this is the silicon crystalline lattice system. So this is the silicon crystalline lattice system. And at room temperature, definitely there is some vibration because these are basically some like spring mass systems. Again, spring mass systems. These are like springs. These bonds are like springs. And silicon atom is like a mass, and these are like springs, bonds. So you have a spring mass systems, and you can basically solve again the equation of motion for it, and you get these displacements, which you call as phonons. Okay, so what happens is that sometimes these springs compress and give rise to a phonon that basically propagate through the entire structure because these springs are connected to each other. So you can have a compression here, maybe you can have a rarefaction here, and you get a kind of a lattice wave, which is basically the acoustic wave, which is basically the acoustic wave. And if you quantize this acoustic wave, I told you in the first lecture also, and you are going to study also the canonical or second quantization in the final lectures. If you use second quantization, you can quantize these in terms of annihilation and creation operator, and you can write basically the energy of these, what should I call, phonons in terms of, let's say, for example, annihilation and the creation operator, which is B dagger B. So you can write it in terms of, let's say, for example, H bar omega Q, B dagger B plus 1, sum over all the phonon wave vectors. Okay, I guess this is H bar omega B dagger B. Yeah, this is N plus 1 over 2. Yeah. So this is basically representing n, which is basically the number of phonons. You will study it in upcoming lectures in the final session. So, but this is the scenario. So these are basically the notions of the phonon. Now this system is also having certain natural frequency, which will be again given by under root of k over mu, the reduced mass. Now here it's the mass of the atoms, mass of the atoms. But these are like the vibrational oscillators, and in this case, because the mu is increased. Why? Because now it is the mu is basically 1 over mass of the nucleus, mass of the atom. So you know that mu increases because there are multiple masses involved. So omega naught basically decreases. And as a result, what happens? The omega naught decreases means the resonance frequency has reduced. Resonance frequency reduces. As a result, incoming frequency, let's say for example, incoming frequency is omega, and that is going to cause resonance only at lower frequencies. Okay, now that means you will have resonance for the vibrational modes only at lower frequencies of the electromagnetic waves. Lower frequencies means, let's say, the infrared, let's say the visible is even higher, let's say the far IR region. So these will be the lower frequencies, or I should say the higher wavelengths. They are going to couple with the system, they are going to resonate with the system. So if you talk about the omega resonant frequency for the phonon, that is going to be much, much less than the resonant frequency of the electron. That is the fundamental notion. Okay, so now another degree of freedom. Degree of freedom means the way a system can move in the three-dimensional space. So one way is electrons can oscillate between with respect to a stationary nucleus. The other way is vibrational oscillations. The other way is you can have a rotational oscillations. You can have rotational oscillations. So you have rotational oscillators. Rotational oscillators are like the rotations of the molecules altogether. Let's say you have a water molecule or any other molecule as such, wherein you can have, for example, if the incoming electromagnetic wave comes in, not directly. So what happens is that there is certain internal rotation of this molecular system, which is basically the rotational motion of the rotational degree of freedom. Okay, so what happens is that if and this will be having certain resonant frequencies. For example, the water, the resonant frequency is 2.45 gigahertz. So if an incoming electromagnetic wave comes at 2.45 gigahertz, it's going to rotate these molecules, and that rotational energy will be converted into thermal energy, and that is going to be basically heating up the system, heating the system. So this rotational energy for different systems is different. Let's say, for example, for nitrogen or for oxygen, for other gases, or for other molecules, it may be different. So that's why they may be having rotational oscillation resonant frequency in, let's say, 40 gigahertz, 45 gigahertz. So it's different for the different systems. Okay, and that is the fundamental of microwave ovens, basically. Microwave ovens. So it heats up the food, and basically the incoming frequency matches with the resonant frequency of the I should say the water molecules. Now you might ask that the same frequency is basically in your Wi-Fi. The Wi-Fi runs at 2.45 gigahertz. The Wi-Fi also runs at 5 gigahertz. So does that mean the Wi-Fi is also causing some kind of a, I should say, thermal energy conversion in the skin or human body? So that is basically rarely that really happens, because the fundamental thing about these frequencies is also something called as power. Okay, it's not only about frequency, it's also about power. So in these communication systems, we try to keep the power levels as low as possible. Low power levels. Ideally zero. Okay, we try to keep the power levels as low as possible because we don't want to heat up the tissue, skin, wherein your mobile phone is, let's say, emitting the Wi-Fi radiations, electromagnetic waves at 2.45 gigahertz. But here the power levels are very low. The power levels are very low, so that it does not heat up the system. That's why in all of your devices you have a rating called as SAR rating, which basically determines how much radiation or how much power it's emitting. So it should be around 1.45. I don't know the units exactly. It's some watt per kilogram, something like that, depending upon the product. But the unit remains obviously same. So it has to be below some 1.5, 1.6 value, and that is what basically we always try. Even for example, your base station, your mobile towers have these horn-shaped antennas. They are emitting these electromagnetic waves. So they also have to make sure that the power levels are very low. Otherwise, definitely they are going to interact with the cellular system, even the tissues, they are going to heat up. But here, in case of a microwave oven, which is almost like if you have an oven, microwave oven, this is almost like a waveguide. Okay, wherein you have microwave sources present here, which are maybe some klystron or klystron guns or something producing the microwaves, and they are getting bombarding your food continuously. Okay, so they bombard your food on all of the directions and cause these, and basically the power level is here. The power levels are more compared to that of the communication system. Obviously, that's why it's able to basically heat up your food also. So it heats up your food and you get a good meal. And now it also depends upon what is the penetration depth of your microwave signal. Okay, so for example, you have one of the questions on the penetration depth. We will discuss in while we solve the questions. Okay, we will discuss about the penetration depth there. Now, if we talk about the free electron oscillator, for example, if you have a metal, in case of a metal, you have a free electrons. You have the free electrons, and you have, and this is also the case in case of highly doped semiconductors, where you have a degenerate semiconductor. Okay, wherein you have the Fermi level almost inside the inside at or above the conduction band of the semiconductor. Okay, that is basically the case of a highly doped semiconductor. It almost behaves like a metal because there is huge concentration of the electrons. So for it, these electrons are not bound. If they are not bound, then the natural frequency is going to be zero. The resonance frequency is going to be zero. What does it mean? It means you have a nucleus, you have an electron, but it's not bound, as if there is no spring. So there is no spring, so it's not bound. It's not going to have the resonant frequency because it's not an oscillatory system just like all other systems. So there is no restoring force at all. No restoring force. Because what provided restoring force? It was the spring. So the spring is no more here. Okay, that means it's not attached to a nucleus. It's almost like a free. So there is no restoring force here. That means if the electron goes here, nothing is going to make it come back. Earlier, if the electron was like this, if the electron went this side, there was a string which we used to bring it back, so it would come back here. But now, if the electron will go in this direction, there is nothing restoring it. So the restoring force is not present there. Restoring force is zero in case of free electrons in a metal. Okay. So now what is going to basically happen? If we talk about now, for example, the Lorentz model, Lorentz oscillator model. So it's just like solving the equation of motion for the electron. Let's say, for example, for the electron, we have the mass of electron, we have the acceleration. It is just like Newton's law, F equals to ma. So that is what basically you need to solve. But obviously, you will have certain damping, you will have certain damping terms, you will have certain restoring forces. So that is basically what you want to solve. So this is F equals, this is the ma, the mass into acceleration, dt square. Okay, plus there will be some damping, which is m times some damping constant dx over dt. This is the damping term. There will be certain restoring term, which is k times x. Okay, so restoring force is F equals to minus kx. Hooke's law, simple. So k you can write as m omega square, m omega naught square into x. So this is basically k, spring constant, equals to minus e times. This is basically the force, the driving force. There has to be certain thing which is driving the system. So all of these things is basically the force. Okay, each of these terms is basically one. It's the force. This is force. This is some force, damping force. This is the restoring force. So this is the acceleration. So this is the let's say mass times acceleration. This is basically some damping force, damping term, and this is the restoring term. And these equations you will find in all of the fields of the engineering, whether it's mechanical, electrical, thermal. These are present everywhere. Even in spin, if you consider the spin of the electron, you have something called as LLG equations. Those are also the similar set of equations wherein you have certain restoring damping forces associated with the spin of the electron. But let's not go into that. So let's say if you talk about the driving force, let's say you have the driving force. I'm trying to be as quick as possible because we have to summarize everything what professor has covered. So if we talk about the driving force is sinusoidal, which is E naught e to the power minus I omega t. Again, we are just assuming a solution here. Okay, it can be either e to the power I omega t, it can be e to the power minus I omega t. Finally, what we are basically going to get is certain changes in the sign of refractive index. A refractive index can be either n equals to n plus I kappa, it can be n equals to n minus I kappa. So it depends upon what are the conventions you take earlier. Whether you took e to the power I omega t, then you will get this. No, you will get this. If you took e to the power minus I omega t, then you will get this. Okay, that is the convention we will get. It doesn't matter. It's going to be just the sign convention change. So you solve the equation of motion. For equation of motion is basically solved for this particular excitation term, driving term, and what you get is that you get a displacement, which is equivalent to E naught over mass of the electrons divided by omega naught square minus omega square minus I gamma omega. So this is the displacement you will get. Okay, so now this is basically what you get is basically you consider the solution to be xt x naught e to the power minus I omega t. So this is basically the solution you consider, and this is the x naught you obtain. Now you put it back, you get x of t to be equivalent to minus e naught over m of e to the power minus I omega t over minus I gamma omega. So this is the displacement of the electron you get. So what happens is that you notice that at omega equals to, let's say for example, this is at omega equals to omega naught, the there is huge response. There is huge response. Okay, this thing basically blows down. And what basically happens now for, let's say for example, for omega less than omega naught and omega greater than omega naught, the x of t is not large. So it only plays a role, it is huge only at this particular frequency when omega is equivalent to the natural or resonant frequency of the system. Okay, so now what is the major goal of it? Why we are computing this? What is the fundamental thing why we are computing this is basically we want to understand permittivity. Permittivity, which is basically epsilon. And now for that, we are going to relate it with permittivity. We consider now, first of all, we compute something called as polarization, which is basically dipole moment per unit volume. And you know dipole moment is if you have a charge, positive charge, if you have a negative charge, and you have a distance L, then the dipole moment, let's say mu d, is basically the charge times the distance. This is the notion of the dipole moment. Let's represent Q as E. This is basically the charge. And if you write n times the polarization, you can have n times the dipole moment per unit volume. This is basically number of atoms per unit volume. Let's remove the volume. So you can have minus n times E x of t, which is basically the displacement or distance between the two atoms. So this will be you can write it as n times E. This x of t we have computed, which is basically this thing. Okay, so you can replace it here. You can write it as in terms of m of e omega naught square minus omega square minus I gamma omega. And now this is basically the polarization you get. And what is basically happening? You see that there are two things. There are two things. One is background polarization. Another is something called as resonant polarization. The background polarization is basically the epsilon naught chi times the electric field. The resonant polarization is basically given as Ne square divided by Me times this particular term, omega naught square minus I gamma omega. So this is the resonant polarization. And you know that electric displacement field is epsilon naught electric field plus some polarization, which can be written in terms of epsilon naught epsilon r into electric field, where this epsilon r is basically 1 plus electrical susceptibility. You know about these things from the Maxwell's equation. Therefore, basically, you can write the epsilon r of omega to be equivalent to 1 plus electrical susceptibility plus, that means this is basically some background term. This is the background term. And then there is some resonant term, which is basically determined as Ne square m epsilon naught 1 over omega naught square minus I gamma omega. So this is the resonant term. And here you have something special, which is basically this particular term, and this particular term is called as omega p, which is Ne square over m epsilon naught. So this is called as plasma frequency. So it's the frequency at which the electron plasma oscillates in a metallic system where you consider the free electrons. And if your incoming frequency matches with the plasma frequency, there is huge absorption. If you have, let's say, a metal, you have electrons, and if the electrons are having certain plasma frequency, which depends upon electron density, which is n,
It depends upon the mass of the electrons. It depends upon the permittivity, that means the medium. It depends upon epsilon naught, which is the permittivity of the medium. So if the incoming electromagnetic wave now hits, if the frequency matches the plasma frequency, you will get a huge absorption of electromagnetic wave. So that is the essence. Other than that, you can get huge reflections. If you saw the reflectivity curve versus the frequency curve, at this particular resonant frequency, at this plasma frequency, below this plasma frequency, you have a huge reflection. At this particular plasma frequency, you have huge absorption. Okay, so that is basically the notion. If your frequency is below the plasma frequency, you will get reflections. But if it's at plasma frequency, then you will get huge absorption in the electromagnetic wave. So that is the concept of plasma frequency. And this is even applicable to understanding certain dielectrics or simpler dielectric models. Okay, so let's say for example you have let me just draw. If you have, let's say for example, you can write for low frequency you can have epsilon omega equals to 0. That means omega tending to 0. You can have two cases, for low frequency and for high frequency. For high frequency, we will say omega tending to infinity. If you put omega equals to 0 in the above equation, which is basically this equation, if you put omega equals to 0, what you get? You get 1 plus susceptibility plus omega plasma frequency square divided by omega naught square. This is what you get at low frequency. At high frequency, if you put omega tending to infinity, just solve it, you will get basically epsilon of infinity to be equivalent to 1 plus susceptibility. That means the epsilon at omega equals to 0 is greater than epsilon at infinity. That is the fundamental notion we understand from it. That means the permittivity at lower frequency is going to be huge compared to that of the permittivity at infinite frequency. So that is basically what is also shown in those curves. If you have the permittivity versus the, let's say, the frequency, let's write it as omega over omega naught. And let's consider some value here, which is 1. That means at this particular frequency, omega will be equivalent to omega naught, which is basically the plasma frequency. Then you will have, you're having either epsilon 1 or you are having either epsilon 2, which is, this is the real part of, let me just denote the color code. This is the real part of permittivity, and this is the imaginary part of the permittivity. And this represents absorption, and this represents propagation. You know it. And now if you draw the real part of the permittivity, let's say this is 0, then it looks something like this, a Lorentzian line shape. Okay, and this width is essential. This width basically determines it can be determined from the damping, which is basically the gamma. Okay, so now what is going to happen if you draw the imaginary part of the permittivity? That is basically going to be something like this, like that, not like this, something like this. Let me draw it like this, something like this. But you have to make sure that epsilon at omega equals to 0 should be greater than epsilon at omega tending to infinity. That is the fundamental notion. So these two values are not same. So this value and this value are different. This is greater, this is lower. That is the fundamental notion. And essentially, basically, you can understand it from just like if you have a the this one, basically if you see the epsilon 1 and if you see the epsilon 2, you approximately see that the epsilon 2 is the derivative of the epsilon 1 with respect to omega around. If you have a function like this, if you differentiate it, its differential will be, this will be peak here, this will be 0 here, it will be something like this. This is basically the derivative of it. Okay, just in order to understand it. And that is basically the notion that if you have, let's say for example, the epsilon to be equivalent to epsilon 1 plus I epsilon 2, then this epsilon 2 is basically the Hilbert transform of epsilon 1. That is basically the concept. And Hilbert transform is basically it's basically phase shifted by something like phase shifted by pi by 2. Okay, so those of you who know about these Hilbert transforms and other things that come in the signal processing, the Fourier transforms and other things, this is just the notion how you basically arrive at these, and how you can even understand it mathematically. Later on, we will basically show it, but this is the notion how you can think about it. Okay, just like if you have, let's say, for example, if this is for example if this is for example a sine function, then this is going to be a, let's say for example if, okay, then this is going to be a cosine function. That's basically what is happening here. If you consider this to be a, like a cosine function, which is given here, then this is around like a, it's almost like a sine function, but it's like a opposite sine function. Okay, that is basically the fundamental notion of it. Just give me a moment. Okay, so I said that this particular width is basically that determines the damping associated. So let's say, for example, this point and this point, this can be, for example, omega minus gamma by omega naught. This can be omega plus gamma by omega naught. So accordingly, you can basically compute the gamma, which is basically the damping of the electromagnetic wave. Now, I'm going to see what else we can cover. Yeah, we can basically think now, if for example we have multiple Lorentz oscillators. So if we have multiple Lorentz oscillators, we can have epsilon of omega to be equivalent to epsilon infinity plus omega p squared sum over all of these oscillators, let's say oscillator 1, 2, 3, so on and so forth, divided by omega j square minus omega square minus I gamma j omega. This is basically omega. So this is the damping for each oscillator. This is the frequency of the each oscillator. Okay, so that is basically the fundamental of this. And this particular thing is called as oscillator strength. Let's not talk about the oscillator strength right now. Oscillator strength. So it's just like the strength of each of the oscillator. I should say how much uh, each of the oscillator couples. That is basically the oscillator strength. But let's not talk about it. Basically, we're definitely going to talk about oscillator strength in the upcoming sessions. And it depends mostly upon whether you have a polar system, whether you have a covalent system, non-polar system. So it depends upon those of the factors. So now what is basically happening is that you have multiple oscillators with, let's say, for example, this is, let's draw a refractive index, and if this is 1. So you have the terms like, you have the plots like this, okay, and then you draw its I should say absorbing part, which is basically just take a derivative of it. That's as simple as that, and you will get peaks, which are the absorbing peaks. Okay, so each of the oscillators is responding at certain, let's say, the certain lower frequency. So that is the fundamental notion of this. So each of the oscillator responds at a lower frequency, but let's say, for example, each response at lower frequency, lower omega, but they don't follow, but don't follow at high frequency. That is the problem. That means if you go omega, let's say in UV region or X-ray regions, those oscillators are not going to behave the similar way, because the frequency there is huge, and these oscillators, they don't follow the high frequency at all. Where basically the here omega becomes much greater than the omega naught. Okay, it only follows at these infrared frequencies or far infrared frequency, where you have a very low frequencies. That is the fundamental notion. And at the important thing is that the two important things are that the two important things, if you note from this, is that at lower frequency, that means omega tending to 0, epsilon of 0 is greater than epsilon infinity, and you have a loss inside the system. If you have a passive system, what is passive? Passive is that you are giving it some form of energy and it's getting absorbed. Instead of if it is active, if in case of an active system, if you give in the energy, that electromagnetic wave is going to get amplified and you will get an amplified response. This is amplification. And this basically happens, I talked about it in the first lecture. This happens in a active medium, which is present in laser. For example, laser. Okay, that is all different scenario altogether. But here we are talking about passive system, wherein you have an incoming electromagnetic wave and decays inside the system. You have a loss. Okay, so there is a loss inside this. So this is basically the passive material. Okay, so now if we talk about, let's say, for example, just quickly move on to the Drude-Lorentz model. Let's say, for example, we talk about Drude-Lorentz model. So this is Drude was a guy, so his name is Paul Drude, and he derived this for basically for metals, how the electrons respond to the electromagnetic waves in case of metal. And for you know that for free electrons gas in a metal, the resonant frequency is zero. I told you because there is no restoring force. No restoring force. Okay. If there is no restoring force, what's going to happen? Nothing can bring the electron back once it is hit by the photon or the electromagnetic wave. And why there is electron gas? Because electrons behave just like a gas molecule with some average kinetic energy to be equivalent to 3 by 2 kT. K where K is basically the Boltzmann constant, in T is the temperature. That's why the name, the free electron gas. It's a very weird name, but that is how the electrons behave, at least up to a first order approximation. So what is basically now happening if you have omega naught to be equivalent to zero, and you know that epsilon omega is basically epsilon omega is this thing, some real part and some imaginary part, and you have epsilon infinity plus the plasma frequency square divided by omega naught square minus omega naught minus omega square minus I gamma omega. This is basically what we derived. Okay, now the plasma frequency is under root of NE square divided by m epsilon naught, and you can simplify this particular term epsilon omega because omega naught is zero. You can simplify this particular equation and you get 1 minus omega square, omega p square divided by omega square plus I gamma omega. So you get the permittivity as a function of frequency in this fashion. Now you can basically get two terms. You can get the real part and imaginary part. You can get the real part epsilon 1 omega, which is basically 1 minus omega p square divided by omega square plus gamma square. You can get the imaginary part, which is epsilon 2 omega to be omega p square gamma divided by omega square plus gamma square. I guess I missed some omega here. I guess there should be one or more omega here. Yeah. So this is basically the real part, which is showing the propagation. This is the imaginary part, which is basically showing the losses or the absorption inside the media. Now, for example, what happens if you have at omega much less than omega plasma frequency? What's going to happen is that, for example, this is the case of lower frequencies. Lower frequencies means infrared or far infrared frequencies of the electromagnetic wave. So there is a lot of scattering of photons. I should say a lot of scattering with photons, not of photons. Okay. So what does it mean? It means that there is, for example, if you have an electron, if you have a photon coming in, electromagnetic wave, so it scatters off the electron. Okay. So there is loss at low frequency. That's what I mean to say. And if you have, for example, if you look at different metals, you will have different loss functions. Loss functions means how much these losses are going to take place or absorption of the electromagnetic waves are going to take place. That is basically represented by gamma, which is the damping parameter. That is what I talked about. Okay, so that is the notion of this. Now, how what does it basically represent? This gamma basically represents the scattering rate. If you talk about, if you go on solving these equations in a real problem, this gamma basically represents scattering rate. So for example, if you have atoms, if you have nucleuses like this, if you have electrons here, if you have electrons like this, if you have incoming electromagnetic wave, this is photon, it's going to give the energy to the electron. Let's say electron goes in this direction, it scatters off the nucleus, and then it goes in this direction, and another photon comes in. It is going to have all this photon electron interactions. Okay, and then this electron is basically going to have excess energy. Then there will be phonons also in the system. So there will be electron, phonon, photon, electron, phonon interaction. So these are complicated processes basically happening inside the metal. And these are, if you want to deeply understand what is basically happening, then you have to invoke the quantum mechanics. Quantum mechanically, they can be solved, and you can solve the Schrodinger equation basically by considering all of those interactions, which is very difficult job to do, even to solve it numerically. But for the Hamiltonian, if you consider the Hamiltonian in the Schrodinger equation, which is the total energy, then it has to consider the electron's energy. Let's say, for example, electron's energy. It has to consider the electron photon interaction. It has to consider the electron phonon interaction. It has to consider the phonon's energy. And then there may be other decaying processes, let's say the phonon phonon interaction. There can be even electron electron interaction. Okay, then there are other those processes. But this is basically the huge Hamiltonian which you need to solve. Even computationally, it's very difficult. People do it, it's a research problem, people do it in different systems. And it takes a lot of time to solve such problems. But this is done quantum mechanically. Definitely, you start with these, then you solve one quantum mechanically, then if you are solving some transport problem, how the electrons transport in certain materials, then you solve something called as Boltzmann transport equation. You can couple this with quantum mechanics, and you can basically see how the losses, how the collision rate, basically the collision rate is the electron collision time is the inverse of the scattering rate. The rate is basically 1/2. So the collision time will be around it's all around 10 to the power 15. Not the collision time, I should say the scattering time is around 10 to the power 15 per seconds. This is the number of collisions happening. That means the tau, which is basically the electron collision time is of the order of around 10 to 40 femtoseconds. So this is the small time in which the electron collision takes place. That means the electron is going here, it's colliding with another electron. That electron is basically getting scattered, and then there are phonons coming into picture. So this is all sorts of mixed up. Just like, for example, electron coming here, it's going here. The electron is hitting. It's coming here. Now the phonon is getting emitted. So you have h bar omega q. This is electron incoming. This is electron outgoing. So now you have all sorts of possibilities which are basically represented by Feynman diagrams. Feynman diagrams. So those are the space-time diagrams which basically represent the losses in the electron energy, how the photons, phonons, electrons interact with each other. And this is basically a problem of quantum electrodynamics, QED. And for that, you have to invoke the deeper quantum mechanics. Okay, so let's not go deeper into it. Let's see, for example, what happens in certain metals. Let's say, for example, if you have an EK of a metal, you know about EK of a metal because you have studied the basic semiconductor course. The E is basically h bar square k square divided by 2m for the free electrons in a metal. Okay, I should call it nearly free electrons. I like to call them nearly free electrons. So you have a parabolic relation. Okay, let me draw it like a parabola. Okay, it's not drawing. Okay, you have a parabolic relation, so you have the Fermi level inside this band, and up to this particular energy, up to this Fermi level, the electrons are completely occupying the states. And once, let's say, a photon comes in with energy h omega, it hits the electron, and it makes the electron to go, let's say, for example, an electron near the Fermi energy to go up in the energy level. Okay, and how much is this? This will be around h omega, which is the energy of the photon. Let's say if this is 2 electron volt, this can go above by let's say for example 2 electron volt. Okay, so then electron will obviously come down back to its original state. There will be electron-electron interactions, electron-electron scattering events that bring the electron back to its original distribution and original state. So if you talk about energy conservation, then you have the incoming energy, or I should say the initial energy plus the energy of the photons that is equivalent to the final energy. Okay, total energy budget. So the initial energy plus the absorbed energy is equivalent to the final energy, which is basically energy at this particular point. And if you want to conserve the momentum, which in this case is very obsolete because the photon doesn't have any momentum. But in case, let's say the initial momentum of electron was h bar ki. This is basically the momentum of electron initially at this particular point. Let's say this is ki. And then it was hit by a photon. Let's say a photon has a momentum ph. Let's consider for time being, and it will be equivalent to h bar kf. Kf is the final momentum, which is basically kf this. You know that this ph is around zero, so you get the final momentum of photon to be electron to be equivalent to the final the h bar ki is equivalent to h bar kf. So that there is basically very small change in k vector of the electron. That is the fundamental point here I want to say. So this is basically the happening at intra-band. Intra means within the band. It's not going to a different band altogether. Okay, just like for example, if you have this metal, you can have other bands as well. There are many bands. We just show only one band. There can be a band here. There can be bands here. There can be bands here. There can be bands here. Okay, this is this is the dispersion diagram of a let's say for example of a typical metal. There can be bands in the up to up to the energy levels you can consider, but there are bands altogether. It's a very complicated system. And if something happens, let's say, for example, this is the Fermi energy, and if something happens, you give so much energy that the electron goes to a different band altogether, then this is basically interband, just like what happens in semiconductors. But if the electron goes to its band, it reaches here, let's say, for example, reach here, this is basically intraband. Okay. And let's say, for example, if we talk about semiconductors, if you have a direct band gap semiconductor, you have electron going from this to this. This is basically interband transition because it's happening between two bands. Okay, it's not happening within the band. So that is the fundamental process. So intra-band absorption processes in metals. So this is basically intra-band absorption in metal. Okay, and it's strong absorption at low frequency. It's strongly absorbed at low frequency. That means IR or near IR regions. Okay, but there can be certain weird ways in which you can have interband absorption as well. Just like for example, if you talk about certain metals, let's say nickel, gold, basically there is d block. These are some d block elements. Then you have a d orbital as well, and there will be contribution in the ek because of d orbitals. Let's say there is a d orbital somewhat like this, and what is basically going to happen, let's say for example d orbital is something like this. Then what's going to happen is the electron from this d orbital can go into the orbitals contributed by the other let's say s or p type states. Okay, then this will be considered as an interband transition, and this altogether changes the properties of the metal. And this is very weird. That's why some of the metals like nickel, gold, and some d block elements, they are very difficult to study even because even the density of the states has a very sharp peaks because of these d block elements. Let's say for example, if you draw the density of states in this direction, this is density of states, this is energy, then you can have density of states like this. But because of d block element, d block I should say d orbital, you can have a density of state peak somewhat like this, which is contributed by the d orbital. Okay, so that means there's a huge probability of finding the electron at these particular place, and the electrons can go to the other bands. If we draw now in terms of the ek, That is basically this particular figure. Okay, this is the density of the states figure for certain metals. So that brings in different properties. Okay, and people are still trying to solve these problems. How to deal with certain metals with d orbital contributions. These are very difficult to deal with. Okay. Now, if we talk about Krammer-Kronig relationships, a brief discussion about what the Krammer-Kronig relationships are. Krammer-Kronig relations. Krammer-Kronig relations are just I should say, for example, you have, for example, the relation between the polarization and the electric field. What is going to happen? So, if you have a certain system, you have certain incoming. You have if you have certain system. Let's say if you have certain system. Let's say this is a black box and its own response is something and you get output and you have certain input, then you can basically for this black box you can write a transfer function which will be basically the Laplace transform of the output divided by Laplace transform of the input. That's it. If you understand this mathematical operation, if you understand the Laplace transforms, you can just play with any of the optical system, and this all everything is based upon the mathematics. Okay, you can have, let's say for example, the electric field can be the input, and you can have the output as, let's say for example, the electric displacement field, and you can have its own function as, for example, permittivity, or you can have, let's say, polarizability or susceptibility. Then all of those things can be done by understanding the transfer function theory. So that's how basically I have understood these. But let's not confuse you with the different notion altogether here. But if you are interested, you can just have a look. If you have studied control systems, or if you have studied Laplace transforms in a better way, you can basically play with these time frequency systems. These are just time frequency systems. So the concept here is that you cannot. There is a concept called as causality. As per the causality concept, basically. So what it says that you cannot have a effect without the cause. No effect without cause. That means if you have, for example, a system, you can have a response at, if you are giving certain impulse response at t equals to 0, then you can expect the response at t greater than 0. There should be no response at this particular t less than 0. So that is the meaning of causality. Okay. So you cannot have a response without the cause. That is the fundamental thing about causality, and it's a very deeper concept. It's a deeper concept. Even in information theory and other things, it's a very deeper concept. But just how you can understand it in layman form. That means if you apply electric field, you expect the polarization. For example, if you have certain system, if you apply the electric field, you expect the polarization to occur. You don't expect the polarization to be already there. So if you write polarization to be epsilon chi of t e of t, so what happens is basically there is a huge misconception around this concept that you cannot write it directly. Why? Because there is certain phase lag associated with the system. Using the oscillator, for example, if you use the oscillator model, you saw that there will be some phase lag because of the masses of the electrons associated with it. So this phase lag basically gives rise to uh, I should say, a delay, okay, in the response, and that basically tells us that you have to have certain correlations with the past. That is the fundamental notion. So that's why you can write, for example, this polarization in terms of space-time function can be basically written as some minus infinity to t integration. It can be written as this particular part. You are familiar with this altogether. This is just like the what should I say? If you write this in this is just like I should say, if you write this in a frequency domain, you can just write it as multiplication in the frequency domain. In the time domain, it is just like a I should say, how should I say, the uh, you don't have a simple multiplication here. Rather, you have certain I should say, there's a certain function which basically has to be integrated with it. Okay, now you, for example, once you solve it, you arrive at relations of chi omega, which is the real part, and chi dash omega, which is the imaginary part. So you get chi and chi omega, and using that, using epsilon omega equals to 1 plus chi of omega, you can obtain the epsilon omega basically. So those are the Krammer-Kronig relationships. That's it. There is no, I should say, rocket science behind the Krammer-Kronig relationships you need to understand. Now, there are certain things which Professor definitely might have covered regarding the odd-even functions. Let's see whether we can cover that in, for example, let's say, for example, you have a simple example. Let's say this is the simple function. You have an amplitude and you have a time here. You have the amplitude time function, and this is for t greater than 0. You can definitely disintegrate into two parts. One will be the just composed of the odd function. Basically, any function is composed of the odd part and the even part. So you can write it in terms of odd function and you can write in terms of the even function. If you Fourier transform the odd part, if you Fourier transform it, you get this particular response, this particular function. And if you Fourier transform the even part, you get this particular function. And if you combine it, you get altogether a spectral amplitude, which is basically the overall response of the system. The spectral amplitude versus the frequency. You are combining these two. The Fourier transform of the odd, the Fourier transform of the even part. That is basically the combined, I should say, epsilon 1 of omega and epsilon 2 of omega. That is the entire notion of the Krammer-Kronig relations. Okay, so that is the fundamental thing you need to understand. And you can definitely check this over. There's a Wikipedia page, very good Wikipedia page where you can check this. These are just mathematical functions where you need to play with them. That's it. Now let's jump into questions of whether we can show and whether we can study. I should say these in whether we can check these in the quizzes, whether we can relate it. Now, for example, the first question is in which region of the electromagnetic spectrum is phonon oscillator dominant? So the phonon oscillator model is dominant for low frequencies, typically, let's say IR or far IR frequencies. And we saw that the natural frequency, resonant frequency for the phonons is much, much less than the for that of the electron case. Why? Because here you have the omega naught is basically under root k over mu. You go on increasing the mu, you decrease the frequency. So this is basically the answer of this question, the infrared. That is the answer of this question. And obviously, because the phonons are associated with heat, and that is also basically a form of infrared radiation. Okay, so heat is like an infrared radiation. That's why you have IR cameras because they can detect the IR radiation, IR electromagnetic wave coming from the human body. So that those are basically detecting the phonons. One important aspect I want to make you understand is that if this is a metal and if this is a semiconductor, the important difference here is that the heat is basically transported by both electrons and phonons. Okay, so that's why there is a separate electronic contribution of specific heat and there is a contribution of lattice specific heat in case of metals because you have here the free electrons, nearly free electron. But if you have semiconductor or dielectric or if you have even insulators, if you have insulators, here the predominant conduction of the heat is by phonons. Phonons. They are responsible for the heat conduction. Okay, so that is the entire essential notion you need to understand. Hardly the electrons play a role in case of heat transport in for the insulators or the dielectrics, except that if it is highly very high doped semiconductor, then in that case it can nearly behave like a metal. But I'm talking about dielectric and insulators. Okay, so you need to understand that. So another question here is that the complex permittivity of water is basically shown, which is just like this molecule. Oxygen has some free radicals and this can rotate. I told you that there is some rotational oscillations or rotational oscillator model we showed. It can rotate around its mean point. So the frequency used in domestic microwave ovens is 2.45 gigahertz. That's what we discussed, which is around this point. Okay, so now identify the type of resonance dominant for cooking in the microwave oven. I told you that the dominant resonance is rotational resonance of the water molecules. Okay, that is the dominant. And the electronic transitions is not possible because why? Because the omega for electronic transition is much greater than the omega naught for phononic. So that is not going to happen because the frequencies here is 2.45 gigahertz, which is 2.45 gigahertz is very low for the electronic transitions or electronic oscillations to happen. Okay, for that the frequency has to be in terahertz at least. This is beyond terahertz, or let's say around 500 or 600 terahertz, I believe. Okay, so this is a very low frequency we're talking about, and that is why there will be rotational resonance of the water molecules, and that results in the heating of the food. That's what we discussed in the initial slides. Now, what might be the reason that microwave ovens are not operated at a wavelength of resonance peak 18 gigahertz, even though the absorption is higher? So they are saying that if you have a, let's say for example, 18 gigahertz, which is somewhat, let's say this is 3, somewhat here. They are saying why don't we operate it here even though we have a higher absorption peak? Higher absorption peak. What is the reason? Why don't we operate it at, let's say, 18 gigahertz? Okay, this sounds logical. So let's see. So there is no source of microwave radiation available at that frequency. Absolutely not. You can make a frequency source at any frequencies. Frequencies above 3 gigahertz are injurious to health, which is absolutely wrong. It depends upon the power level. I talked about it. The penetration depth of microwaves will not be enough to go through the food will create excessive on-surface heating. Okay, so that sounds interesting. So let's look at it. What does it say? If you have an oven and if you have microwaves coming coming in from all the sides to your food, and if you have food in a container which is like this, let's say your food is like this up to this depth, this is the depth of the food you want to heat. So the microwaves should basically go through this food in order to heat it, okay, entirely. Otherwise, what is going to happen? It's going to heat up only the surface, and the bottom part of the food will not get heated. And what will it depend upon? It will depend upon penetration depth. Penetration depth of what? Of microwave, obviously. And we have talked about that if you have the refractive index to be n plus I kappa, you can write absorption coefficient mu as 4 pi kappa divided by lambda. Okay, so this is the absorption coefficient. And if you want to write the penetration depth, you can write delta to be equivalent to lambda over 4 pi kappa. This is the penetration. This is the absorption coefficient written in per meter, and this is the penetration depth written in meters. Now see what is going to happen. If you have 2.45 gigahertz and if you have 18 gigahertz, in case of 18 gigahertz, you're increasing the frequency. That means you're reducing the wavelength. So if the wavelength reduces, the penetration depth reduces. Okay, so if the penetration depth reduces, the microwaves will not penetrate deeper to food. Okay, so that means it's not going to penetrate deeper into the food and only the surface is going to heat up and bottom of the food will remain colder. There will be huge resonance near the surface, but because of the penetration depth, it won't enter the deeper levels of the food, so the food will remain colder there. So that is basically the reason why you cannot just choose any of the frequency because you need to take care of the penetration depth as well. What is the fourth option? This frequency is reserved for military usage. I don't know as such. Microwave ovens will be more expensive. I don't know. These don't sound logical. This one sounds logical. And I told you that these are injurious to health is not a concern because it obviously depends upon the power levels. Otherwise, the frequencies of the Wi-Fi and as well as the microwaves are the same, but the power levels in case of a Wi-Fi are very low, ideally zero. You can talk to communication people more about what do usually they use the power levels in case of a communication systems. Now, if you have you need to describe the scattering phenomena. Scattering is the electromagnetic wave once it encounters any of the disturbance, it scatters, just like it disperses. Okay, now there are three types of main scattering. One is Rayleigh, second is Raman, third is Brillouin scattering. First of all, Brouillard scattering is inelastic. That means there is energy loss slash gain. There is change in energy. Raman is also inelastic. The Rayleigh scattering is elastic. That means there is no change in the energy. So whatever the photon is coming in, the incoming photon and outgoing photons are having same energy. But here in Raman, incoming photons and outgoing photons are having different energy altogether. That is the same case here. Okay. Brouillard scattering mostly occurs if there are some lattice waves present. If you have a medium and if you have incoming electromagnetic wave, if you somehow induce, let's say for example, phonons inside the system, and if you have a density gradient variation, these are basically the acoustic waves, what you call phonon, you can have a change in, I should say, you can have this phenomenon of what is called as Brouillard scattering. So it's like a photon phonon interaction. So interaction happens. So you have, let's say, incoming. So let's say you have, let me draw it like this. You have incoming photon and you have incoming phonon. So what is going to happen? Let's say photon goes in this direction and it changes energy. If this is h nu I, if this is h nu f, so overall total energy will be h nu f will be some h nu I plus h bar omega. This is the energy of the phonon. So there will be overall change in the energy. Similarly, what happens in Raman? The similar phenomena are involved, but there's a different frequency range involved. Different frequency range involved, and they are mostly, basically they target the vibrational and rotational transitions of the molecules. But this basically targets, I should say, the lattice waves, which are mostly phonons, polaritons, magnons. I have talked about it in the first lecture. Similarly, Rayleigh scattering is also elastic. There is no change in the incoming photon, and although it scatters because of the density fluctuations or the refractive index fluctuations, but this is because of incoherent or heat or incoherent fluctuations inside the medium. This is more like a coherent fluctuation, what you have induced. Okay, so as a result, there is energy change, as well as there is, in this case, for example, in the Rayleigh case, there is momentum change of the light also. So that is the fundamental option. That's the answer of this question. So the Rayleigh scattering is elastic, and the momentum of the light changes. Okay, so that means if the light was going in this direction, so there may be final change in the momentum in the change in the momentum of the light in a different direction. That means the k will change, but the energy is going to remain same. Energy will remain same. That's it. And calculate the plasma frequency of a silver metal Ag in electron volts, given its free electron density. This is given. The mass is given. Epsilon is given. You can compute the plasma frequency as n e square over m epsilon naught. Everything is given. You can use the electron density as n, and you can use mass as this particular value, which is 1.1 times the free mass of the electrons, and you should get the value as 8.95 electron volts. So this is the plasma frequency. That means if you have silver, and if you have reflectivity of a silver versus the frequency, let's say frequency by plasma frequency, then this curve will look something like this. At exactly, let's say if this is 1, at omega equals to plasma frequency, there will be huge dip, there will be huge absorption around the plasma frequency. And in this region, the entire silver will behave as reflective. Okay. And in this region, there will be huge absorption at omega equals to omega plasma frequency. That is the fundamental notion. So this is basically energy, and you can convert energy to frequency by using this relation. You will get the frequency to be around, I don't know how much this is. This is such a huge frequency. This is like 8.95 eV. So if you know, I know that 3.81 eV is around 325 nanometers. So this is huge frequency. This is around 900 terahertz, I guess. So this is a beyond 1000 terahertz frequency. I don't know. Okay, that's a huge frequency. So now the complex refractive index of a gallium arsenide. You need to compute the complex refractive index of gallium arsenide. And this gallium arsenide has a band gap of around, I guess, 1.2 electron volt. I'm not sure. The wavelength is this. This is given. The absorption coefficient has to be computed. So this is basically the kappa attenuation coefficient. Attenuation coefficient. And you know the absorption coefficient mu is 4 pi kappa divided by lambda. So everything is given. You get absorption coefficient as per meter. You can compute the value. Just put it there and you will get the exact value. So if we do 4 into 3.14 into 0.243 divided by 532 into 10 to the power minus 9. Okay, so this will be 4 into 3.14 into 0.243 divided by 532 into 10 to the power 9. So you need to solve this and you will get the exact answer. Okay, so it'll be around I guess for 10 to the power 6. So they don't sound logical, or do they? Yeah, they don't sound logical. So there will be something like in terms of these will be the answer of this question. So you just need to solve this equation. So that's about this. Now let's consider two schematic band structures of, for example, the silicon and gallium arsenide. This is for silicon. This is for gallium arsenide. So this is a direct band gap semiconductor. This is an indirect band gap semiconductor. That means if the electron goes here, a phonon comes in and it can bring the electron here. Okay, it's like a phonon mediated, phonon assisted absorption. So this is like phonon assisted absorption. And now in order to understand it in for example, some simplistic models, you need to consider the energy of the phonons. You need to consider how the absorption takes place because of the phonons. But here it's directly, the electron goes directly here. If the electromagnetic wave comes in, the electron goes to the higher energy state. So what is it shown? We have to select the correct statements. In a direct bandgap semiconductor, momentum is conserved when an electron makes a transition between bands, and in direct bandgap semiconductor, it's conserved by simultaneous absorption and emission of phonons and photons. Okay, so we're talking about first direct bandgap semiconductor, and then there is indirect bandgap semiconductor. For the direct bandgap, it's saying that momentum is conserved when electron makes transition. That's absolutely true because the momentum is conserved means they are at same k value. The k value is not changed in case of direct bandgap semiconductors. If this is, let's say, k1, the electron goes to a higher energy state, but with the same wave vector, k1. But the energy changes, obviously. Okay. So, and in indirect bandgap semiconductor is conserved by simultaneous absorption and emission of phonons. But if you have indirect semiconductor, so if this is k1 wave vector, this is k2 wave vector, electron goes initially to up to this point, then there is a phonon coming in or any other mediated particle, is quasi-particle, it brings the electrons to this particular K2. So there is, I should say, it is conserved by emission or absorption of phonons. So the overall, so for example, overall, this is the overall wave vector, just like a vector algebra. So this is H. Let's say let's call this. Let me write it like this. Let's call this K final. This is K initial. This is K. Let's call it K. Let's not call it K. Let's call it Q, which is the wave vector of phonons. So you can have K final to be equivalent to K initial minus Q. Okay, so that is the conservation of momentum is definitely always there because it's conserved because of some other mediated intermediate quasi-particles involved. Either it can be photons, it can be phonons. Most of the time it's phonons because a photon cannot just change the momentum of the electron. Okay, so this is basically here you need to consider something called as electron phonon interactions, and that is I should say my research topic. I study these electron phonon interactions experimentally in case of certain polar semiconductors, gallium nitride, uh, aluminum gallium nitride, and this is a very hot topic because these electron phonon interactions are present in every device, and you want to control these electron phonon interactions in order to make better efficient devices for you want to understand them even for thermal efficiency. Okay, so that's about this. So the S1 seems to be correct. What other things is correct? In indirect semiconductor, momentum is conserved by photon emission, and indirect it is conserved by both. No, this is absolutely wrong. Recombination is more efficient in gallium arsenide than silicon, hence used for optoelectronic devices. Absolutely, because this is a direct bandgap semiconductor and this is an indirect bandgap semiconductor that I talked about. So there will be more, I should say, the transition from direct bandgap semiconductor directly gives you light, but for the indirect bandgap semiconductor, you get light, but you also get certain losses, which is usually in the form of heat, which is basically the phonons. You don't want those heat to be, you don't basically want heat in your LEDs. So that's why the LED is made up of silicon heat so much. So they require a heat sink so that they can dissipate heat. So heat sink is basically that is the heat is basically a problem in case of silicon based or indirect bandgap based optoelectronic devices. So the answer of this question is this. Now the easiest question, two graphs showing the variation of electric field as it propagates through different media. Based on these graphs, we need to determine the nature of the medium. So this seems to be a lossy medium. This seems to be a lossless medium because the amplitude is staying same. Here the amplitude is exponentially decaying. So it's like e to the power some exponential e to the power minus x times sine of omega t type of function. This is remaining sine of omega t. There is this particular loss term. So the graph A represents lossy medium where the wave undergoes attenuation, and graph B represents lossless where the wave doesn't undergo attenuation. That's absolutely correct. And here, if you would see that the epsilon will be having epsilon 1 plus I times epsilon 2. So this term will be large here. But in this case, the epsilon 2 will be small, or even epsilon 2 will be 0 in this particular case, which is basically showing the losses inside the medium. Okay. Now this question, it says that a graduate student performs a spectroscopy experiment and measures the absorption coefficient of material X. There's a material X. Certain people do spectroscopy experiment where they pass light and they compute the reflection, they compute the absorption, they compute the transmission. Okay, how it is done, that's a different story altogether. The imaginary part of permittivity determined from major absorption spectra is given. Choose the correct profile of the real part of the permittivity corresponding to the measured imaginary part. Just answer. So this is basically epsilon. This is basically the imaginary part of the epsilon, imaginary part of epsilon omega, which is basically showing the losses or the absorption. Okay, now I told you that if you are given one of these, you need to just do Hilbert transform. That is just a cool trick, but it's mathematically valid. You can just differentiate it. If you differentiate the black curve, you will get something like this, and something like this. So this will be wider, this will be sharper, and what is the one that is matching? That is this one. So this is the exact answer of this question. So you have epsilon of omega to be equivalent to epsilon 1 of omega plus I times epsilon 2 of omega. So if you are given epsilon 2, you can compute epsilon 1 by just d epsilon omega by d omega. So it's not exactly right. Basically, you need to shift it, Hilbert transform it by, or change the phase by pi. That is basically what you mean to do the Hilbert transform. If you check the mathematics of what professor might have done, that is basically the same concept of Hilbert transform. That is the fundamental notion. So this is not correct. This obviously is not correct because you need to have a change at that particular frequency in the propagation in the epsilon in the real part of the permittivity. And this is wider here and narrower here, which is obviously not going to happen as per the given loss function. So option A using the Krammer-Kronig relation is the correct option. Now this is basically for the optical engineered materials. So optical engineering of the materials, we engineer three things: epsilon, mu, and n. This is permittivity. This is permeability. We have not talked about permeability. Basically, it's related to the magnetic properties of the material. That's why initially when we talked about the oscillator model, when we talked about the oscillator model, we talked about the nucleus, we talked about the electron. And then we talked about it is in the presence of an electric field, which is a time varying electric field. But We didn't talk about the magnetic field. Magnetic field is also there because you have an electromagnetic wave. And apart from electromagnetic field, this is B field, this is E field. There is magnetic moment associated with the electron. What is that magnetic moment? That is basically magnetic moment. That is basically there is some spin associated with the electron that can respond to the magnetic field. Okay, now, and it's present in all of the materials. Now, certain materials have definite permeability value. Most of the materials you see will be having mu equals to 1. That means they are mostly non-magnetic. But there are certain materials, definitely ferroelectric materials, ferromagnetic materials, where you have a large value of mu. In that case, you cannot ignore it. Why you cannot ignore it? Because the refractive index is actually epsilon times mu. It's not only under root of permittivity. And this mu, if it is large, then refractive index is going to be large. Similarly, you can have epsilon to be epsilon 1 plus I epsilon 2. You can have mu to be equivalent to mu 1 plus I mu 2. Okay, just like you the this shows you the propagation of the electric field component of the electromagnetic wave. This shows you the loss of the electric field component of electromagnetic wave. Similarly, this shows the propagation of the magnetic field component of electromagnetic wave, and this shows the loss of the magnetic field component of the electromagnetic wave. That is the similar notion. This is for electric field, this is for the magnetic field. Okay, and now once you have it, let's say you have epsilon to be equal to epsilon 1 plus I epsilon 2, you have mu to be equal to mu 1 plus I mu 2. You can write it in terms of a phasor. You can write it epsilon to be equal to some, let's say epsilon naught e to the power I theta. You can write mu to be equal to mu naught e to the power I phi. And you can write, even you can write the refractive index to be under root of epsilon naught mu naught. This is magnitude e to the power I phi plus theta divided by 2. Okay, this comes because of the square root. And you can show them on a unit circle. A unit circle. And this is basically the imaginary of, let me show all of them together. Imaginary of epsilon mu refractive index. This is the real part of epsilon mu refractive index. Now what is the game? The game here is to tune these all of these properties together in order to have different responses altogether. That is the fundamental notion of optically engineering materials, or even the concept of metamaterials comes because of it. Let's say, for example, you have, certain, for example, if you talk about lossless metal. In case of a lossless metal, you have, for example, mu is equal to 1. So mu equals to 1 you show on the real axis only, and you will be having the epsilon to be equal to some negative value. Let's say it's equal to epsilon 1. Then what will be the, just give me a moment. I guess I have lost the connection. So what will be the I should say uh, refractive index? That will be this particular average. So the refractive index is here basically n1 plus I times n2. So the n1 is 0, but n2 is non-zero. So that is a 0 refractive index. And you see, where is the ambiguity? The refractive index 0, what does it mean? That means if the velocity inside the medium is equal to c over n plus I times kappa, so this is 0. That means you get velocity to be equivalent to this particular value. And what will be the velocity of the electromagnetic wave inside the metal then? Obviously, you know that the velocity cannot exceed the velocity of light. So just think about it, what's going to happen. The maximum velocity has to be the velocity of light. So this is how we can tune. So now you can have altogether different configurations of epsilons and the mu's, and you can tune the refractive index. What is the question here saying? The question here is saying is that the values that gives rise to a 0 refractive index is, so the value that will give rise to a 0 refractive index is if the mu is 1 and the epsilon is basically minus times epsilon 1. This is basically negative epsilon materials. Negative epsilon materials. So the answer of this question is part C. Okay, similarly for this, let's say this is some mu which is equivalent to mu naught e to the power I phi. So this is some epsilon naught e to the power I theta. So the n will be around here. This will be n naught e to the power I theta plus phi divided by 2. Okay, this will be the negative index material. Negative index material. Now, what does that mean? Negative index material. It's like the this is for, let's say, the material with magnetic response. Magnetic response. That means you have certain mu permeability value. Okay. Similarly, if you talk about this, the refractive index will be positive. It will be in this particular direction. Similarly, for this, the refractive index might be here, and altogether you can just change or tune the refractive index as per this. So that's the whole area of what you talk about metamaterials, where you basically tune these permittivity, permeability, and the refractive index in order to design certain materials which can do things as per your will, because nature does not have this is very weird, but nature does not have everything that can satisfy humans. So humans want to make certain things which can satisfy themselves, so that's why we are just inventing meta materials. Okay, so that's about this lecture. It's been a quite interesting session, and we have tried to cover everything that professor has covered in the week. So if you just go through this lecture, you might be able to understand most of the things that professor has tried to cover. So I'll be trying to stop this recording. Uh, Hope to see you next week around the same time. Thank you.